Welcome to the chapter on structural engineering. Understanding the fundamentals of structural engineering is crucial for ensuring the safety and stability of structures like buildings, bridges, and tunnels. In this chapter, we will cover the essential components of structural engineering, including beams and columns, load-bearing structures, and foundation systems. Beams and columns are essential components in structural engineering. They are used to support loads and transfer them to the foundation. A beam is a structural element that primarily resists loads applied laterally to the beam's axis. These loads create bending moments, shear forces, and deflections in the beam. There are different types of beams, including simply supported beams, cantilever beams, and continuous beams. Each type has its own characteristics and applications. The bending moment, denoted as M, and shear force, denoted as V, in a beam are critical for its design. For a simply supported beam with a point load P at the center, the bending moment M is given by the formula M equals P times L divided by 4, where L is the length of the beam. The shear force V is given by the formula V equals P divided by 2. A column is a vertical structural element that primarily resists axial compressive loads. Columns are crucial for transferring loads from the structure above to the foundation. There are two main types of columns: short columns, which fail primarily due to material failure or crushing, and long columns, which fail due to buckling. Buckling is influenced by the column's length, material, and cross-sectional shape. The critical load at which a column will buckle can be calculated using Euler's formula. The formula is P sub CR equals pi squared times E times I divided by KL squared. Here, E is the modulus of elasticity of the material, I is the moment of inertia of the column's cross-section, K is the effective length factor, and L is the unsupported length of the column. Load-bearing structures are designed to support and transfer loads safely to the ground. These loads can be static, such as dead loads, or dynamic, such as live loads. There are various types of loads that structures must support, including dead loads, which are permanent, live loads, which are temporary or movable, wind loads, and seismic loads. In load-bearing structures, loads are transferred from the point of application through various structural elements to the foundation. For example, in a building, slabs transfer loads to beams, beams transfer loads to columns, and columns transfer loads to the foundation. Foundations are critical for transferring the loads from the structure to the ground. They ensure stability and prevent excessive settlement. There are two main types of foundations: shallow foundations, used when the soil near the surface has sufficient bearing capacity, and deep foundations, used when the surface soil is not strong enough to support the loads. The bearing capacity of soil is the maximum load per unit area that the soil can support without failure. It can be calculated using Terzaghis bearing capacity equation. The equation is Q sub alt equals Cn sub C plus gamma D sub Fn sub Q plus 0.5 gamma Bn sub gamma. Here, C is the cohesion of the soil, gamma is the unit weight of the soil, D sub F is the depth of the foundation, B is the width of the foundation, and N sub C, N sub Q, and N sub gamma are bearing capacity factors. For a shallow foundation with a cohesion of 25 kilopascals, a unit weight of soil of 18 kilonewtons per cubic meter, a depth of foundation of 1.5 meters, and a width of foundation of 2 meters, with bearing capacity factors N sub C equals 30, N sub Q equals 18, and N sub gamma equals 15. The ultimate bearing capacity is calculated as follows. Q sub alt equals 25 times 30 plus 18 times 1.5 times 18 plus 0.5 times 18 times 2 times 15. This results in an ultimate bearing capacity of 506 kilopascals. This calculation ensures that the foundation is designed to support the loads without failure. By understanding these fundamental concepts in structural engineering, first-year civil engineering students can begin to appreciate the complexities and importance of designing safe and efficient structures.